The next technique to learn is the linearization technique. We will first learn the linearization technique, and then as we learn the BCV technique, we will see that the BCV technique can be combined with the linearization technique to be able to utilize the linearization technique to the fullest. So the linearization technique is to use a proximal term to cancel out computationally inconvenient quadratic terms. Let's see an example. Imagine we have an update of this form. So we minimize the xk plus 1 iterate is defined through this argument. We minimize f of x plus this quadratic term involving the matrix A, and then this proximal term involving the metric matrix M. Now let's assume that our function f is a proximable function, and we also assume that we are given the freedom to freely choose any positive definite metric matrix M. If that is the case, we make this particular choice m is equal to 1 over beta I minus a alpha times A transpose A, and we assume that 1 over beta is bigger than the alpha times the largest eigenvalue of A transpose A. This condition ensures that the metric matrix M is positive definite. So with this choice, we take this objective and then we simplify it. So this is the objective in the argument defining xk plus 1. We expand this quadratic term, and when we do so, we get the cross term, and then we have b alpha over 2 times b squared, but that's a constant that does not depend on x, so we ignore that part. And then we have the alpha over 2 times x transpose AX. So this is a quadratic term in terms of x. And then we expand this term. So this term has an xk m norm squared, but that term does not depend on x, so we ignore that. This norm has a cross term, so x inner product x transpose mxk, so we have this term, which is linear in x. And then we have the quadratic term, so we have 1 over 2 times x transpose mx. Okay, so these two, the left-hand side and the right-hand side are equal, except for constants that do not depend on x. And then here, we plug in m is equal to 1 over beta I minus A transpose A. So when we do that, and then we collect the linear terms, we get, this is the term linear in x. And here's another term that's linear in x that comes out as a consequence of having 1 over beta I. And then here we have alpha over 2 x transpose AX. And then here, again, here we plug in this definition of m. And note that this part, the part that has minus A transpose A, cancels out this term. So this term vanishes, and then the term involving 1 over beta x squared remains. Now we take this term and pull it into here, and then except for a constant that does not depend on x, we get this equivalent form. And now we can write this, we can complete the squares and write this in terms of a form that resembles what we would see in the definition of a proximal operator. So xk plus 1 can be defined as the argument of this thing, and this is the proximal operator of beta with respect to beta f, with this provided as input. So we have this, xk plus 1 can be computed with the proximal operator with respect to beta f, and with this expression that can be evaluated using matrix vector products. So to reiterate what the idea is, we carefully choose the metric matrix M in the proximal term so that we are able to cancel out this quadratic term, x transpose A transpose AX, this inconvenient quadratic form which originated from this term. When we carry this out, the result is as if we linearize this quadratic term. So this quadratic term is an inconvenient term because it produces the x transpose AX quadratic term. So instead of dealing with this quadratic term as is, the result can be interpreted as we take the first order Taylor expansion of this quadratic term about the point xk, so that gives us this. And then, but instead of then performing the argument, we add this type of this quadratic proximal term in order to ensure convergence. And hence, this technique is referred to as the linearization technique, as it can be interpreted as linearizing an inconvenient quadratic term. Let's see a more concrete instance of this. So we'll use the linearization technique to derive the linearized method of multipliers. So we start with this function, this optimization problem, where we minimize f of x subject to the linear equality constraint ax equals b. Now we can apply the method of multipliers to solve this problem, but before we do that, we will first perform a change of variables. So we let M be an arbitrary positive definite matrix, and then we let K be another positive definite matrix defined through this relationship. So we multiply 1 over square root of alpha, and then we multiply the inverse of the matrix square root of M. Then given this matrix K, we reparameterize that problem. We perform a change of variables into the variable y. So we say x is k times y, and now we can express the optimization problem in the changed y variable. And these two optimization problems are equivalent because K is an invertible matrix. So now we apply the proximal method of multipliers to this reparameterized problem. So the proximal method of multipliers, remember, involves minimizing the augmented Lagrangian. So this is the augmented Lagrangian of the reparameterized problem with a quadratic proximal term. But the proximal term in the proximal method of multipliers, at least as is, has the regular norm squared rather than the m norm. So this is the proximal method of multipliers applied to the reparameterized problem. But now that we've obtained the method, we revert the reparameterization and then go back to the x variables. So we substitute back x is equal to kx, and then we get this. So now we went to the y variables, applied the proximal method of multipliers, and then reverted back the change of variables. And the result of that is that we get the matrix M here. If we had not done this, if we just apply the proximal method of multipliers directly to the original problem, then instead of getting the metric M here, we would have just gotten the regular norm square. So now, through this reparameterization, now through this trick, we are able to get this metric matrix M, but this choice is arbitrary so long as M is positive definite. So we make this choice, M is 1 over beta I minus alpha A transpose A, subject to this condition to ensure that the metric matrix M is positive definite. Then we perform the linearization reasoning, we perform the calculations, and we get this. So this quadratic term, the quadratic part originating from this term, the x transpose A transpose AX, that term gets canceled out. So now we are left with this term, which is linear in x. We are left with this function, which is assumed to be proximable. And then we have this quadratic term, which no longer involves a metric m, but rather just the regular norm square. This argument can be interpreted as a proximal operator, and when we carry out the calculations, we can express our algorithm in this way. This method is referred to as the linearized method of multipliers. So if total duality holds, alpha and beta are positive. If this step size condition holds, then the primal iterates converge and the dual iterates converge. The linearized method of multipliers is useful when the proximal operator with respect to beta f is easy to evaluate, but this argument, the argument that has this inconvenient quadratic term, if this argument is not easy to evaluate, then the linearized method of multipliers becomes a useful method. Next, let's talk about the BCV technique, the final technique of this chapter. When we were using the linearization technique, we relied on the proximal term of this form, and this form had to come from somewhere. In the previous example, the proximal term came from the proximal method of multipliers, but in general, we can use the BCV technique to create these type of proximal terms. The name BCV is the abbreviation of the name of the three authors Bertsikas, O'Connor, and Vandenberg. This technique, the BCV technique, was originally presented by O'Connor and Vandenberg in what I refer to as the primal form in their paper, and essentially concurrently was also presented by Bertsikas in his book in what I refer to as the dual form. Let's use the BCV technique to provide an alternate derivation of the method PDHG. Again, we consider the optimization of the form minimize f of x plus g of ax. The first step of the BCV technique is to consider this equivalent problem. Let's look at it in detail. So in the original optimization problem, we were minimizing with respect to the variable with respect to the variable x, which is of length n. We still have that same variable here. But in the first step of the BCV technique, we introduced this additional variable x tilde, And x tilde now enters this optimization problem. But x tilde, which is of length m, is constrained to be 0. So this is the indicator function with respect to this set 0, the singleton containing 0. And so this indicator function constrains x tilde to be equal to 0. But when we when we consider the function g, instead of saying the function is g of ax, we say the function is g of ax plus m square root x tilde. So m square root is an arbitrary positive semi-definite matrix. So the matrix square root exists, and then we provide the x tilde here as the input. Now, because x tilde is required to be 0 by this indicator function, we can basically ignore this term, and so this function, which we define to be as g tilde x comma x tilde, is essentially the same as what we had before, g of ax. So now we used to have the optimization problem of minimize f of x plus g of ax with the variable x. But now we have the optimization problem of minimize f tilde plus g tilde, where the optimization variables are x and x tilde, and these two problems are now equivalent. In the next step, we apply DRS to this equivalent problem with f tilde and g tilde, and we apply the reflected resolvent with respect to f tilde first. The fixed point iteration maps from zk comma z tilde k to zk plus 1 comma z tilde k plus 1. Now, the reflected resolvent with respect to f tilde is rather straightforward to evaluate. The reflected resolvent with respect to g tilde requires a little bit more consideration. So the way we do so is we use this identity, which we had proved before. So the proximal operator with respect to alpha times h composed with the matrix B can be evaluated by first performing this minimization problem, where we minimize h conjugate with these additional terms. And then we perform this matrix vector product and vector subtraction. So this identity applied to our function g tilde provides us with a formula to evaluate the proximal operator with respect to g tilde, where the input is x comma x tilde and the output is y comma y tilde. The way we do so is we perform this minimization problem, where we minimize g conjugate with this inner product. So this is linear in U, and then with this quadratic term. Then once we find the argument U, then we perform these matrix vector products, and then use that to compute y and y tilde. This formula does require this regularity condition, so we will assume it. So now, utilizing this formula, we can write out the fixed point iteration with respect to the DRS operator. So this is the proximal operator with respect to f tilde, this is the proximal operator with respect to g tilde, and this is the z update. Note that because f tilde is basically just f of x plus delta of 0 x tilde, the proximal operator with respect to f tilde is really simple. We just evaluate the proximal operator with respect to f, and then the x tilde is just identically equal to 0. Now let's further simplify this. Note that the zk plus 1 and z tilde k plus 1 updates have already been simplified by plugging in x tilde k plus 1 half, x k plus 1, and x tilde k plus 1. So these three variables, x tilde k plus 1, x k plus 1, and x tilde k plus 1 half, there no longer is any explicit dependence in this iteration. So these three variables can simply be removed. Next, to simplify the xk plus 1 half and uk plus 1 updates, we will take the zk plus 1 definition and plug it into here with the index decremented by 1. And then here, when a z tilde k appears and when zk appears, we will take the definitions of zk and z tilde k and plug them into here to eliminate the explicit dependence on the z variables in this argument and this argument. We do that and we collect the terms and simplify things a little bit, and we get this update. So xk plus 1 half is defined in this way with this dependency on the previous xk 1 half and then the uk iterate, but with no dependency on zk or z tilde k. And the same is true with uk plus 1. So the dependency is on the xk plus 1 half iterate, and then the previous xk iterates, and then the uk iterate, but there's no dependency on the z or z tilde iterates. Furthermore, we use this matrix norm notation to simplify things a little bit. So this two-line expression describes fully the fixed point iteration with the DRS operator in this setting. Now, in order for this iteration to be more computationally efficient, what we can do is we can choose the M matrix so that M is equal to 1 over alpha beta times identity minus AA transpose, so that the AA transpose cancels out with this. And then we choose the step size alpha and beta sufficiently small so that this condition holds, which implies that the matrix M is positive semi-definite. And then we are left with this iteration. So here, the definition of xk plus 1/2 was already within a form of a proximal operator with respect to f. So we simply write that down here. The uk plus 1/2 update was originally not in the form of a proximal operator, but by defining M to be of this form, this becomes the Euclidean norm. And then by collecting terms and moving things around and simplifying things, we can write the update in the form of a proximal operator with respect to beta times G star. So let's conclude. If total duality holds, this regularity condition, which we assumed along the way, holds. If alpha is positive, beta is positive, the step size alpha beta satisfies this condition so that the matrix M is positive semi-definite holds, then the xk plus 1/2 iterate converges to x star. We provided an alternate derivation of PDHG as an instance of DRS. As before, at this point, the bulk of the convergence analysis has been completed, and now all that remains is careful bookkeeping. In this case, let's briefly go through the bookkeeping that allows us to establish the convergence results. Let's consider this Lagrangian L tilde. This Lagrangian L tilde generates the stated equivalent primal problem, and it generates the dual problem of this form. If the original primal dual problems for PDHG has a primal solution x star, a dual solution u star, and strong duality holds, then the equivalent problems have the solution x star comma 0, and then the dual solution of this form. And it is relatively straightforward to check that for the original primal problem with solution x star and the equivalent primal problem with solution x star comma 0 have the same primal optimal values. And the original dual problem with solution u star and this equivalent dual problem with this dual solution, they have the same dual optimal value. And therefore, for the equivalent primal dual problem pair, strong duality also holds. So again, this is the type of reasoning that we underwent when we were analyzing the convergence of ADMM. And the conclusion is that if total duality holds for the original problem, then total duality holds for the equivalent problem. So now it is safe for us to assume total duality of the original problem and conclude that DRS converges for the equivalent problem under the stated assumptions regarding the step sizes and the regularity condition. Using the BCV technique, we provided an alternate derivation of PDHG. Next, let's use the BCV technique to derive a new method called PD3O. We consider the optimization problem of minimizing f of x plus g of ax plus h of x. Here we assume that of course f and g and h are all CCP functions, but we furthermore assume that h is a differentiable function. This is in fact the same exact problem setup that was considered in the Condot-Vu algorithm. We use the BCV technique to obtain this equivalent problem. So again, we add the additional optimization variable x tilde, which is of length m, and we add the indicator function with respect to the set 0 to constrain x tilde to be 0, and then we add the m matrix square root of m times x tilde, and then we just add in the h of x, and the h of x function is remained unchanged. We define this function to be f tilde of x tilde, x and x tilde, this function to be g tilde of x and x tilde, and then we define this to be h tilde of x and x tilde, even though there is no dependency on x tilde in this term. We use the DUIS FPI, and the fixed point iteration maps from zk z tilde k to zk plus 1 z tilde k plus 1. So this is essentially the same as before, except now instead of using DRS, we are using DYS to accommodate the third differentiable function h tilde. as before, we carry out the calculations, and we use the metric matrix M to be a 1 over beta alpha identity minus A transpose, the same matrix that was considered in the derivation of PDHG, and we get this algorithm. This algorithm is referred to as the primal dual 3-operator splitting, or PD3O for short. The two methods, Condot-Vu and PD3O, both solve this same optimization problem. Condot-Vu generalizes PDHG, whereas PD3O generalizes PDHG, but it also generalizes PAPC at the same time. The Condot-Vu method has this form. So remember, so again, Condot-Vu generalizes PDHG. So if we were to eliminate the H function, then we would recover PDHG. But in the case of Condot-Vu, we have the function H, so that enters here. In the case of PD3O, PD3O again also generalizes PDHG. So if we were to remove these H functions, then we would recover PDHG. But PD3O is different from Condot-Vu in that not only do we have this additional term, but we also have this term where we add grad H xk minus grad H xk plus 1. So seemingly, PD3O is slightly more complicated than Condot-Vu in the sense that it requires a few additional characters in describing the algorithm. Computationally speaking, however, the implementation, the execution of these two algorithms, Condot-Vu and PD3O, essentially require the same amount of computation because at every iteration, the gradient of the function h is evaluated once, and in the case of PD3O, the grad h of xk plus 1 is evaluated here once, and then it is also reused again in the next iteration. The convergence criterion of the two methods slightly differ. So for Condot-Vu, it is this criterion, whereas in PD3O, it is this criterion. And if we compare the two, Condot-Vu has these two quantities added being less than 1, whereas in PD3O, the quantities individually are required to be less than 1. So PD3O has the more relaxed, it has the more generous, therefore the better step size requirement. And roughly speaking, because PD3O allows the two terms individually to be less than or equal to 1, PD3O accommodates step sizes that are, roughly speaking, twice as large. And in some cases, this difference does lead to PD3O being, roughly speaking, twice as fast as Condot-Vu. So far, we've used the BCV technique to derive the method PDHG and PD3O. Those instances of the BCV technique are what I refer to as the primal form of the BCV technique. Let's use the dual form of the BCV technique to derive the method Proximal ADMM. So we consider this optimization problem. This is the optimization problem that was considered in the ADMM setup, where we minimize f of x plus g of y, where x is of length rp and y is of length q, and the x and y variables are coupled. They are related to each other through this linear equality constraint ax plus by is equal to c. So this is the optimization problem, and then we consider the positive definite matrices, positive semi-definite matrices m and n, and then we define p with using alpha and the matrix m, and then q with the scalar alpha and the matrix n. The dual form of the BCV technique is to consider this equivalent problem. So in addition to the original variables x and y, we introduce the additional variables x tilde and y tilde. And the x tilde and y tilde variables, they do not appear in the objective, but they appear in the constraint. So the original constraint ax plus by is equal to c remains the same, but we add two additional linear equality constraints saying that px plus y tilde is equal to 0, and then x tilde plus qy is equal to 0. So the x tilde and y tilde in this case, they are not constrained to be equal to 0, rather they are constrained to be equal to, y tilde is constrained to be equal to minus px, and x tilde is constrained to be equal to minus qy. But in any case, it doesn't really matter what x tilde and y tilde are required to be, because they do not enter the objective function. All that is required is that it's always possible to find a feasible x tilde and y tilde, and that certainly is the case. So this original problem is equivalent to this alternate equivalent problem. Now let's apply ADMM to this alternate problem. So when we apply ADMM, well, now that we have the x and x tilde variables, the first subproblem solves for x and x tilde, and then the second subproblem solves for y and y tilde. And then now that we have three equality constraints, we have three sets of dual variables. So we have the UK dual variable, which corresponds to the original equality constraint, ax plus by minus c is equal to 0. And then we have the second dual variable, u tilde 1, which corresponds to the equality constraint px plus y tilde is equal to 0. And then we have the second dual variable, u tilde 2, which corresponds to the equality constraint x tilde plus qy is equal to 0. In writing this down, I have skipped some tedious calculation steps, but let me point out a few important points. So the x tilde update is expressed in this way, and because this minimization is a quadratic minimization problem, we have a closed form solution. So x tilde k plus 1 can be written in this way. And the same is true with the y tilde update. So the y tilde update is quadratic, so we can write down the closed form solution. And if you think about it, the fact that x tilde and y tilde updates have a closed form solution is not surprising, because there's no objective function corresponding to x tilde and y tilde. There's only the linear equality constraint. So really, it of course the minimization of course should be quadratic, and there of course should be a closed form solution for x tilde and y tilde. So x tilde and y tilde has this form, so we plug this this closed form expression into x tilde and y tilde whenever they occur in order to simplify our iteration. So when we plug in y tilde into the definition, the y tilde u tilde 1 update, it turns out that u1 tilde is always equal to 0. And if we plug in x tilde into the u2 update, it turns out that we always get this thing. Since u1 tilde is equal to 0, we plug it into here to basically eliminate this term. Since u2 tilde has this form, we plug this into here and thereby remove the need to keep track of explicitly u1 tilde and u2 tilde. And here y tilde k occurs, so here we plug in this form. And then here x tilde k plus 1 occurs, so we take this and plug it in, take this expression and plug it into here. So carrying all of this out one by one, we arrive at this final form. So the x update, x plus 1, k plus 1, is obtained by solving the argmin with respect to the augmented Lagrangian with this additional proximal term. The yk plus 1 update is obtained by minimizing the augmented Lagrangian with this additional proximal term, and the uk update is performed in the usual way. Remember, the m and the n positive semi-definite matrices arise because the P and Q matrices were basically defined as the matrix square root of the M and N matrices, respectively, then scaled by 1 over alpha. So here we have Px norm squared, so that squares that P matrix, and that's why we get the M matrix here. And in the Y update, we have the Qy, and that is squared. So the Q squared, that basically gives us the N matrix. Let me quickly correct a typo. There should be a factor alpha here. Okay, so this method is a re-derivation of the proximal ADMM method, an alternate derivation of the proximal ADMM method. And if total duality holds, M and N are positive semi-definite if this regularity condition holds, and if this regularity condition holds. So these are the regularity conditions that ensure that the ADMM method applied to the equivalent formulation converges. And if alpha is positive, then the primal dual iterates converge, the primal iterates converge in this sense, and also the y iterates converge in this sense. So now we have the proximal ADMM method derived using the BCB technique. Next, we'll use the linearization technique to obtain linearized ADMM from proximal ADMM. So again, we consider this optimization problem, and we apply proximal ADMM with this metric matrix M and this metric matrix N. So we plug in these matrices and perform some simplification steps, which does require some laborious calculations, but once we carry that out, we get this for our X and Y updates. And then now that the only quadratic term is just the Euclidean norm squared without any additional matrices, we can write these arguments as the proximal operators. So now this three-line expression describes linearized ADMM, where in the first step we perform a proximal operator with respect to f. In the second step, we perform a proximal operator with respect to g, and then in the third step, we perform the usual dual update. And this method is referred to as linearized ADMM. If total duality holds, alpha, beta, gamma are all positive, the step sizes satisfy this condition and this condition, then the primal iterates converge and the dual iterate converges. Finally, let's provide yet another, a third derivation of PDHG. So we again consider this optimization problem, but now it's written in a different way. So this optimization problem is minimize f of x plus g ax, but instead of writing g of ax, we write it using this linear equality constraint. Now this problem is more in the ADMM form, so we can apply linearized ADMM to obtain this method. Now this method does not at first sight seem to resemble PDHG that much, but if we make the particular choice beta is 1 over alpha, and then if we use the Moreau identity to convert the proximal operator with respect to g to the proximal operator with respect to g star, then we perform some change of variables, some calculations, then we arrive PDHG. So we recover PDHG. So again, if total duality holds, alpha and gamma are positive. If this step size condition holds, then the dual iterates converge and the primal iterate converges. All right, let's conclude this chapter. So in this chapter, we analyze convergence of a wide range of splitting methods. And at a detailed level, the many techniques that we discussed are not at all obvious, and they do require many lines of laborious calculations. However, at a high level, the approach is to reduce all of the methods to a fixed point iteration and then apply theorem 1, the convergence of the average fixed point iteration, to ensure convergence. So given an optimization problem, which method should you choose? Because at this point, upon completing listening to this lecture on Chapter 3, or upon completing reading Chapter 3, you might come out with the impression that there are way too many methods for one to choose. But in practice, a given problem usually has at most a few methods that can be applied conveniently. So the different splitting methods discussed in this chapter, they all assume different problem structure. So given a particular problem structure, there's only a handful that would fit your particular problem. A good rule of thumb is to first consider methods with a low per iteration cost. Analyzing how many iterations of a given method are required for the method to converge to a desired accuracy, that is more difficult to know a priori, but identifying the per iteration cost of each method is a much more easier exercise. So it is a good idea to first figure that out, the per iteration cost of each method, and then try out methods with a lower per iteration cost first.